Okay, let's look at question 5 from November 2018. This is a reaction rate question. The reaction of zinc and excess dilute hydrochloric acid is used to investigate factors that affect reaction rate. The balanced equation for the reaction is zinc plus 2 hydrochloric acid goes to zinc chloride plus hydrogen gas. The reaction conditions used and the results obtained for each experiment are summarized in the table below. The same mass of zinc is used in all the experiments. The zinc is completely covered in all the reactions. The reaction time is the time it takes the reaction to be completed. Now, before we look at the table here, I want you to have a look at this. Excess dilute hydrochloric acid. This means that zinc is the limiting reagent and the reaction has gone to completion, okay? So in theory, in all of these measurements in the table, the reaction is finished. We can't argue that the time is longer or the time is shorter because the reaction didn't finish. It's told you there's excess acid, the reaction is completed, okay? So this is why this is fair to say that this is a measure of reaction rate. So in this table, we've got 5 different experiments. So when I look at a table like this, I always look to see what's been changed, okay? So we've got 2 concentrations. All of a sudden, number 3's got a very high concentration. This has got a lower concentration, so it goes high, low, very high, low, high for concentration. Then if we look at the volume, 200 cubic centimeters, 200 cubic centimeters, 200 cubic centimeters, 400 cubic centimeters, and then 200 cubic centimeters. Now, it says to you there's excess acid and the reaction is completed. So this one here of 400 cubic centimeters, this one's really weird because you actually don't need excess. So like they've more than doubled, or they've doubled the amount of acid, but in all of these they were excess anyway when they were 200. So this is just randomly weird, and it's probably somewhere later in the question related to something. Then we've got the state of division of the zinc, powder, granules, powder, granules, powder. We know that theory says that if we divide a solid up into powder, the reaction will continue faster. So if you have 2 things that are identical, then the powder will go faster than the granules. Then if we have a look, the temperature of the acid, 25, 25, 25, 25, 35. This is the only one where we've increased the temperature of the reaction vessel. And then the reaction time. And obviously you can see this one is the fastest. The second fastest is this one, which is not a surprise because it's got the huge concentration. So let's go have a look at the question after we've tried to understand what's going on in the table. It says experiment 1 and experiment 5 are compared. Write down the independent variable. Now remember that this independent variable, independent I, what did I change? Okay, so if we look at number 1 and number 5, the concentrations are the same. If we look at the volume, the volumes are the same. If we look at the state of division, the powder and powder, they are the same. In 1 and 5, if we look at the temperature, the 25 and 35. So my independent variable here, it has to be temperature. That's the only reaction condition that I have changed in order to carry out this reaction. Okay? Then define reaction rate. Change in concentration of products or reactants per unit time. You need the change, this word change in concentration of products or reactants, and you need per unit time. Okay? Write down the value of X in experiment 4. Experiment 4, what's going on in experiment 4? We've got 1.5 molar hydrochloric acid. We've got, this is the one with a big volume of hydrochloric acid. We've got granules. We've got temperature. How are we going to find this value? To find this value, we have to figure out which experiment is the same as this and take the value from the experiment that's the same as this. So we need something that's got a concentration of 1.5. Look, here's number 2. And these are comparable because they are both granules. They're both at the same temperature. So X is going to be 14 minutes. X is going to be 14 minutes because remember I said to you when we looked at this that why have we got excess? This is the volume. Don't confuse your volume and your concentration. This concentration and this concentration in 2 and 4 are exactly the same. This just means we chucked excess acid in. So the amount of time for this reaction to go to completion is going to be exactly the same as reaction 2 because all of the other reaction conditions between reaction 2 and reaction 4 are the same. Now it says to you, can we get the table and this in the same field of view? Okay, I need the table and the graphs. It says to you, the Maxwell-Boltzmann energy distribution curves for particles in each of the experiments 1, 3, and 5 are shown below. Identify the graph A, B, or C that represents the following. Okay, before I even go and do this, I look at the graphs and make my own conclusions from the graphs before I look at the reactions. So if we look here, this solid curve and this curve A, their peak is in the same place. So A and B has got the peak in the same place. C has got a lower peak and it's further to the right. Can you see C here? Has got a peak to the right. These two have got the same peak to the left. So immediately, because most particles in C have a higher kinetic energy, temperature is the measure of the average kinetic energy of the particles. So C is going to be the high temperature curve. So I'm telling you that C is 5. So I'm going to put C here because I've worked it out already in my brain. Okay. Now let's have a look what's going on with A and B. These two are at the same temperature. We've got all of the rest of the graphs here at the same temperature. And then what is going on, the difference between A and B? B has got a lot more particles in it. Can you check here if you read off the number of molecules axis? B has got a lot of molecules, A has got fewer molecules. So this one must be at a higher concentration than that one, because this y-axis reading is telling you the number of particles and the x-axis reading is telling you the temperature. So in here, B must be a higher concentration. So they've given us the choice of 1, 3, and 5. 1, 3, and 5. Now 3 is the one with a very high concentration of hydrochloric acid. So this has got to be B as far as I'm concerned, because it's got a massively high peak showing you that we've got a lot of particles. So, excuse me, identify the graph that represents the following. Experiment 3. So experiment 3 is the high concentration. So we agreed that is B because the graph shows a high number of particles, indicating the high concentration of acid in experiment C. Okay, this is only 2 marks, so maybe we don't have to bring the temperature nonsense into this. Okay, experiment 5. Experiment 5 is the high temperature one, graph C. Okay, graph C shows a higher average kinetic energy for the particles. The peak of the graph is at a higher temperature. Okay, you should go back when you've done this and check the memo for the proper wording, the exact wording of how to phrase this. The reasoning is correct. Just check and see, go through the questions and see what kind of language they like you to use. So there's a higher average kinetic energy of the particles here. The peak of the graph is at a higher temperature. Okay, it says to you, experiment 6 is now conducted using a catalyst and the same reaction conditions as for experiment 1. What is the function of the catalyst? What do we ever use a catalyst for? A catalyst is used to speed up the rate of reaction. How will the heat of reaction, this heat of reaction is the other name for delta H, how will the heat of reaction in experiment 6 compare to experiment 1? You can only change the heat of reaction by changing your reactants and products, so it must be equal to. The catalyst is going to do absolutely nothing to your delta H. Your delta H is going to remain the same. Calculate the average rate of reaction in moles per minute with respect to zinc for experiment 2 if 1.5 grams of zinc is used. Okay, if we need moles per minute and we've got grams of zinc, first problem, we need the number of moles of zinc. How do we find the number of moles of zinc? We use that formula, M over M, but you know I can't write the over in here as a fraction, so I'm going to write this as a, what you call that thing, a division sign. What is my mass that they gave me? 1.5. It's divided by the molar mass of zinc. Have you got your periodic table? Looks like it's 65. So with your calculator, 1.5 divided by 65, I've got 0.023 according to my calculator. Please be checking me with your calculator. So the number of moles of zinc is going to be 0.023 moles. Okay, and now we want the average rate of reaction for experiment 2. So what is the time, the delta T for experiment 2? What does experiment 2 say? Experiment 2 says 14 minutes. Okay, what unit does it say? We must use moles per minute. So average rate of reaction is the change in concentration of reactants. Okay, the change delta. You struggle with the delta here. The change in concentration of reactants over the change in time. So we went from 0.023, okay, went from 0.0. Okay, because we're doing change in reactants, you know what I've forgotten to write here? This is supposed to be negative, okay? So it's going to be minus the final, which is 0, minus the initial, which is 0.023, and this is going to be over the change in time, which is 14 minutes. Okay, so calculators, 0 minus 0.023 is 0.023 divided by 14. I've got here 1.64 times 10 to the power of negative 3 moles per minute, yes? And I do believe that's your final answer. Let me just format it nicely for you. So there would be my average rate of reaction. Finish and klaar.